To simplify a radical, we want to write the radical in such a form that the radicand has no factors other than 1 that are perfect squares. The radicand is the number inside of the radical sign, so in the first example the radicand is 10. In the second example the radicand is 50. In the first example 10 has no factors other than 1 that are perfect squares, so it's already simplified. But for the square root of 50, we do have a factor that's a perfect square, a factor of 25. So we need to take that square root of 25 out of the square root of 50 to simplify. I rewrote this square root of 50 as the square root of 25 times the square root of 2, in which in the first radical sign I have the perfect square. In the second radical sign I have whatever's left over, the other factor, to multiply by the 25 to get 50. If I simplify that first radical, I have 5. And I can't simplify the second radical any further, the square root of 2, because it has no other factor in it besides 1. That's a perfect square. If you recognize a perfect square that divides into your radicand, then you can carry out the problem in this manner. But let's say that you don't recognize that the square root of 25 is a factor of 50, or 25 is a factor of 50. In that case, what you can do is prime factor 50. I'll use a factoring tree for this one. 50 can be written as 2 times 25. 2 is a prime number. 25 can be factored down into 5 times 5. So the square root of 50 can be written as 2 times 5 times 5 in prime factored form. Since I'm talking about the square root in this case, I can take out 2 of the 5's that are inside the square root and bring them outside of the radical sign as a single 5. In other words, the square root of 25 is 5. Factoring in this fashion can help you to recognize or help you to get to the simplified version without necessarily recognizing what the perfect square is in a radical. Let's look at another example. The fourth root of 128. In this case, it might be hard to recognize a perfect fourth root that divides into 128. But if we factor 128 into prime factors, we may be able to pull out the perfect part. In this example, instead of the tree, I'll use what I call inverted division, an upside-down division, in which I'll divide by prime numbers continually until I end up with a prime number at the end. In this case, 128 divides by 2, giving me 64. I'll divide by 2 again, giving me 32. I'll divide by 2 again, giving me 16. I'll divide by 2 again, giving me 8. Divide by 2 again, giving me 4. And divide by 2 again, ending up with 2, which is prime. So 128 can be written as 1, 2, 3, 4, 5, 6, 7 2's. Since I'm talking about the fourth root, or looking at the fourth root of 128, I want to take 4 of these 2's out as a single 2 in front of the radical. And I'm left with 3 2's multiplied together, giving me 8. Since 8 doesn't have any perfect fourth roots in it, seeing that from the 3 2's, there aren't 4 of them, this would be the simplified form of the fourth root of 128. Let me give you one to practice. The cube root of 80. Use either method. Pause the video, come back to it when you're finished to check your answer. For this problem, I will simplify it through prime factorization. So if I divide by 2 to get 40, divide by 2 to get 20, divide by 2 to get 10, divide by 2 to get 5. 5 is prime, so I'm finished with the prime factorization. I have 2 times 2 times 2 times 2 times 5. Because I'm taking the cube root of 80, I want to take out 3 2's as a single 2. And I'm left with the cube root of 10 on the inside. So the simplified form of the cube root of 80 is 2 times the cube root of 10. Let's look at another example. The square root of 150. Solve this by either method, or simplify it by either method. Pause the video and come back to it to check your answer. For this problem, I recognize that 25 is a perfect square that divides into 150. 25 times 6, so I broke this into the perfect square times what's left over, the other factor, to give us the product of 150 when multiplying by the perfect square. And if I simplify further, the square root of 25 is 5, square root of 6. We can also work with variables. For example, let's say my expression, my radical looks like this: 72 x cubed y squared z to the 5th. And I want to simplify that. If I expand this into prime factored form, if I divide by 2, divide by 2 again, divide by 2 again, now divide by 3, my radical becomes the square root of 2 times 2 times 2 times 3 times 3. If I expand my x's, expand my y's, and expand my z's, my radical would look like this. Because we're taking the square root, I want to take out pairs of numbers and variables that are the same. So I can take out 2 2's, 2 3's, 2 x's, 2 y's, 2 z's, 2 z's again. If I take each of those out as a single value or variable, I would have a single 2, a single 3, a single x, a single y, z, and then z again from each of these pairs of z's, all on the outside of the radical. And on the inside, I'd be left with the 2, an x, and a z. If I simplify the outside, 6xy z squared times the square root of 2xz. If you notice from the beginning, this 72 can be broken into 36 times 2. The square root of 36 is 6. And here's the square root of 2. X cubed is not an even power. Looking for even powers because of the square root. But I can take 2 of those x's out as a single x, which is what I did. And if I do that, I'm left with a single x on the inside. The square root of y squared, that being even, I can take all of them out as a single y. Z to the 5th, the perfect square that is less than z to the 5th would be z to the 4th. I can take out z to the 4th, or take the square root of z to the 4th, which is z squared on the outside, left with a single z on the inside. And let me give you one practice problem of this type. The cube root of 128, a cubed, b to the 5th, c to the 7th. Stop the video, simplify it with either method. When you're finished, come back to check your answer. In this example, I'll work it by taking out the perfect cubes of each of these factors. In the first cube, I'll put all the perfect ones. For example, a perfect cube that divides into 128 is 64. It'd be 4 cubed times 2, which is the factor needed to multiply by 64 to get 128. I have a cubed. I'm looking for the cube root, so I can take all 3 of them and put them in the perfect cube. B to the 5th. B cubed would be the largest perfect cube less than b to the 5th, so I can take out b cubed here, and I'm left with b squared in the other radical. C to the 7th, the largest perfect cube less than c to the 7th, is c to the 6th, leaving me with a single c in the other radical. If I take these cube roots, I would have 4 a b c squared, the cube root of c to the 6th would be c squared, times what's left over, the cube root of 2b squared c. So again, in simplifying a radical, we want to make sure that the radical that we're left with has no perfect, has no factors that are perfect cubes or squares or whatever radical we're working with. In this last case, our cube root that we're left with has no perfect cubes in it, and so the form is in simplified form.